Hello, everyone. Welcome to our Lab 1. This is going to be an introduction to measurements. In this lab, we will learn about data analysis tools, some sort of like a statistical tools that you will be using when dealing with experiments. Because physics is experimental science, most of the experiments require measurements. And then, we let's say trying to verify some kind of physics concept. What we do, we set up an experiment, take measurements, do some calculations, and then look at our result and try to see if that result matches our predictions. So most of the time in this class, that's what we will be doing. We're going to be, learning about the concept in the lecture portion, and then in the lab, we will be doing experiment to verify some of those concepts, some of those predictions, and obviously they all require measurements. So this lab allows us to look at some of those statistical tools that we will be using. So how do you make measurements? What do you do with your measurements? How do you calculate your result? How do you present your result? All of those things can be, more or less learned in this chapter, in this lab 1. All right, so let's start with, something simple. So let's say, think of something that we want to measure. And there, you can have infinite amount of things, let's say, you can think of, right? Let's say you can measure a length of, I don't know, a pen or a pencil that is in front of you. You can measure the length and width of a table in front of you. You can measure then, let's say, the time it takes for you to go to, let's say, from home to school. There's so many things that you can sort of like, let's say, measure. Remember, there are several fundamental units of measurements that we learn in the lecture class, and those are length, mass, and time. And one of the things we do here is with those 3 measurements, right? So we can then later on calculate a number of other things like speed, like acceleration, force. That means doing just those 3 simple measurements in terms of time, length, and mass, we can calculate then a lot of other things. So that's why in this particular lab, what we will do here is we're going to look at in terms of just measuring a length of something. Okay, so again, you can think of anything, let's say, in front of you, but I'm going to give you an example. Let's say there's a table in front of you. Here's a table. Okay. So let's say those are the legs of the table. Okay. And one of the things we can do here is we can measure the length and the width of a table. So let's say, let's take this side to be the length, and then this side to be the width of the table. Okay, so your task, let's say, is to find length and the width of the table. Number of things you can do is you can then go, take a measuring tool. Obviously, you're not going to look at it and try to guess what's the, the length of it, which you can, but it's just not accurate. So what we do, we use some kind of appropriate tool. For example, a meter stick in laboratories, let's say whenever we have a face-to-face class, in laboratories, I do give students a meter stick, and I tell them to go and measure the length of a table. Now, what they do here is the meter stick basically is 1 meter long. Sometimes they need to, measure, maybe use a measuring tape rather than meter stick, because measuring tape can be 2 or 3 meter long. But let's say right now here is 1 meter stick is good enough. And we have a table that, let's say, part of group of 4 students going to be measuring those dimensions of the table. Now, what you do here is you take the meter stick, you approach the table, and then you use the meter stick to measure the length of the table. And let's say you record your measurements as here's the length is equals to, let's say your measurement is 82.1 centimeters. Okay, so technically whenever we're using meter stick with centimeter units, there's 2 significant figures after the decimal point needed to be taken into account. So because meter stick has precision of 1 centimeters, which means the tenth of a centimeter. That means that those little marks in the meter stick, those are centimeter apart. Okay, so that means the tenth of a centimeter then technically is a direct measurement, but then after that, anything else is pretty much an estimation. Okay, so for example, let's say I have 82.12 centimeters of measurement. Now, from here, then what we can do is we can try to then figure out, is this measurement correct or not? How do we figure out if this measurement is correct or not? Well, maybe the second person in your group can take the meter stick and go and measure the same thing again. Verify your measurement. That means then you're going to get the second measurement of the same thing, which is the length of the table, which means now you have 2 data points. Okay, so then we can say that this is length 1, then this will be length 2. Okay, for example, then when the second person makes the measurements, one of the things that always happens is the measurement is slightly different. Very, very rarely you're going to have 2 people measuring the same thing and they end up with exactly the same, for example, 82.12. Second person will get maybe 82 let's say 18 centimeters. Now, what we have then is we have 2 numbers, slightly different, but very close to one another. And this is sort of like, let's say, one of the things you're going to be doing, because when you have one measurement, what if you measured it wrong? So then what we do here, we measure it again and again and again and again to have a confidence in our measurements. So let's say then this is L1, this is L2, then you have a third person measuring L3, maybe that person has 82.25 centimeters, then the fourth person, let's say this person maybe will have 82.65 centimeters. And as I said, right, there's always a little bit of, deviation of the numbers, and that's normal. This is expected because in every experiment, when you take experimental data like this, by the way, this is known as a data set. Okay, so whenever you take a data set, there will always be a little bit of discrepancies between numbers. Why? Because there are what we call errors involved with any measurement. Error doesn't necessarily mean it's a mistake or it's a wrong answer. It just means that, error is always sort of like a built-in part of the measurement. And there are 2 types of errors. So let's look at in terms of errors. There are 2 types of errors. So we have random errors, which are generally human-made errors. And there's also a systematic error. So systematic error those are usually equipment-based errors. So let's say you didn't calibrate your equipment correctly, or you didn't, you're not using the correct equipment and things like that. So that means systematic errors is sometimes, let's say, can be corrected by calibrating. Let's say, for example, you want to have object, move on a flat surface. You can make sure that it's a flat surface, right? So you basically make sure that flat surface and, change it if it's not. And as soon as you have a flat surface, then you can eliminate, so like, let's say the systematic error based on the fact that you might have a slight incline compared to, a flat surface. So that's something that can be corrected. Human-made errors cannot be corrected because those are the type of errors that come from, just the reaction time and things like that of person. And if you have several people doing the, taking the data set, then you have some people who are, a little bit better at the reaction, some people are not. But the idea here is that that's kind of always expected. That means if you're taking a data set, even the same person, right? If you if it's just you doing the, like let's say 5 to 10 measurements of the same thing, at the end, you're going to get tired. You might not be as accurate, let's say, as, you were at the beginning. So random errors always has to be taken into account. Systematic errors can be corrected. Okay, now let's look at this. You have a data set now, 4 measurements of the length. What will be the next step as a group? Well, next step is you don't want to come to me and tell me that, okay, so we have 4 measurements of the same thing. You can go ahead and choose which one you want. No, what you do as a group, you take that and basically make it as a table of measurement. You can say, okay, here's my measurements of length, so L, in units of meters. And then what we have here is we then have some trials. That means, for example, then here's trial 1, L1, and that was 82 point, let's say 12. And then here's trial 2, which is 82.18. Sorry, the unit's actually centimeters. And then L3, 82.25, and L4 is 82.65. That means you get a data table like that. The next, as a group, what you would do here is you need to then find the best way of presenting this data for the length of the table. And to do that, we're then going to be using 2 types of statistical mathematical tools. The first one is we're going to calculate the average. Or another name for this is the mean. Okay. So average, or the mean of the data set, is calculated by, let me give you some, like a standard equation. So let's say you have this quantity X that you're measuring. So then this quantity X always comes with a data set, because this is a type of, statistical tool that is used specifically with some kind of quantity that can be measured directly. Length can be measured directly because you can take a meter stick, measure it directly. So then finding the average for this type of quantity, let's say this quantity X, we put like bar on top of it, indicating that this is a calculation for the average of this quantity X. And this equation is just equals to the first trial measurement plus second trial plus that, and n trial. You have n number of trials. So for example, our number of trials 4, but you can have 5, 10, 20, 30, depending how accurate you want it. And then divided by n, which is then the number of measurements. Okay, so in this particular case, it will be adding all the measurements and dividing by the number of measurements that you have. Okay, for example, for us, it will be length average equals, so measurements of length 1 plus length 2 plus length 3 by 2, 3 meaning the trials, plus length trial 4 divided by number of measurements. For us, it was 4. So this will be 82.12 plus 82.18 plus 82.25 plus 82.65, and then divided by 4. And then I can put just parentheses and put like they're all in centimeters, because this is a measurement. This is not just a number. This is not just 82.65, it's 82.65 centimeters. All right, so then calculate the length. All right, so calculating at the top, I get 329.2 centimeters and divided by 4, which will give me 82.3. Okay, so now, generally, I would like to put another extra digit here to match whatever I have. At least you need to have same amount of decimal points or decimal values as your data. The standard for the average is to put maybe one extra, let's say decimal value. So, but mine is 0, so I can just put another 0. But the idea here is that, let's say 82.30, 300 or 30, technically for us exactly the same. But let's say this is what we have. So this is our average value for the length. That means from all of those values, 82.300 centimeter represents the best possible measurement value. But here's the thing, right? This is not a measurement directly. Technically, this number that we just calculated is not a measurement. It's the calculated value from your measurement. So average is not a measurement, but actually it represents the best possible value from your data set. So, and this is just one number. That means you can come to me and tell me, okay, so our best guess for the length is 82.300 centimeters. Okay, but now, as a group, you also understand that there was some deviation of each data point compared to the, let's say, one, to the values, right, compared to one another. And that was because of the random errors. That means one of the things we can do here is that we can say, we can take that into account by calculating, let's call this, equation 2, by calculating the, what we call uncertainty, or mathematical term for that is standard deviation of your data set. That means the equation, remember, so this is technically the general equation for the average. And then I apply that to the length. Okay. Now, let me give you the general equation for the uncertainty or the standard deviation for some quantity x. It means sigma x is equals to, so the standard deviation basically comes like this. It's a square root of, then what you have here is your first measurement, x1, that means your first data point, minus the average, then you square this, plus the second data point minus the average, then you square that, plus the third one minus the average, you square that, plus then that. So your last measurement, nth measurement, minus the average square, everything inside the square root, and then this whole thing divided by n minus 1, which is number of measurements minus 1. So that's the general equation for the standard deviation. Standard deviation equation. In physics, we usually call this uncertainty. Okay. That means how certain you are about your data set. And generally what we have here is you can sort of like, let's say, have a reliability or certainty about your data set when you calculate the uncertainty. So for example, then for us, it will be uncertainty of not x, but let's say length. And this is equals to, then square root of, open the square root. So at the top, then we have our first measurement. So this will be 82.12 minus our average, which is 82.300. We square that. Plus then the second measurement. If you want, as I said, right, you can just put the centimeters inside next to each one. So then 82.18 centimeters minus the average, 82.300 centimeters square, plus that. So then do the same thing for the other two measurements, and divided by number of measurements is 4, so it's n minus 1. So 4 minus 1, basically divided by 3. Okay. So if we do that, then we can get the uncertainty of, all right, so we get 0.1718 centimeters square, because we're squaring, right? Divided by 4 minus 1, which is 3. Okay, so divide this by 3. So then we get square root of 0.057 centimeters square, and then take the square root of that. So we get 0.24 centimeters, and that will be my answer. Okay, that means then what I had, this was my average, and then this is my uncertainty. Okay, now why did we need to do that? Because again, any data set has this random errors. People make mistakes. So when you come to me and tell me, okay, so I have the measurements of length. So when you have a measurement of length, then what you want to do here is you want to say, all right, so here's my length measurement. That means L is the, your measurement. My best guess here is that the value of length is the average value that we got. Okay, but technically then this measurement could have been as large as for example, let me put it like this, right? So was 82.300, but it could have been as large as this number plus 0.24. And the reason is because, there were uncertainties involved, right? Or it could have been as low as minus this number, 0.24. That means what we can say here is that, our measurement has a best possible value, which is the average of the data set, but it also can be plus minus the uncertainty that we, calculated because of the random errors. And this is how we always make a measurement. So for example, some kind of measurement X, then you present it as this is our best possible measurement value for that quantity X, which is the average, but then plus minus uncertainty of X represents that, as an experiment, you can never have 100% measurement value. There are always uncertainties. There are always, some kind of errors involved, and this represents that. So X bar plus minus sigma X represent that. That means here I can say L average plus minus sigma L, which is basically, 82.300 plus minus 0.24 centimeters. Let's not forget that. And that's how you would present as a data to me. That means average plus minus the uncertainty or the standard deviation. Okay. So it's not necessarily that difficult in terms of, let's say, when you look at those equations, you guys use once or twice, it's going to be relatively straightforward. But the idea here is, in a way, for any type of direct measurement, let's say experimental direct measurement, right? Those are the only two things, sort of like, let's say, you need to do in order to do the data analysis. Find average, find uncertainty, and then you can present your data. And then you can say, those are my measurements. So my length, right, is 82.300 centimeters in terms of the best possible value, but plus minus the uncertainty of 0.24 centimeters. Okay. Now, how about the width of the table? If I go back here, look at the width of the table, same thing. You would get a data set, right? So you have the measurement of one person does that. So it's a little bit shorter. So maybe about, I don't know, maybe like, let's say 38.25 centimeters. Second person, maybe 38.45 centimeters. The third person, 38.12 centimeters. Fourth person, maybe even, let's say 39.10 centimeters, something like that, right? So you get 4 measurements. What do you do? Well, you find the average, you find the uncertainty for the width measurement, right? And then say, average plus minus uncertainty then is your measurement of the width. And you can come to me and then present your data. Okay. That means anything that you measure directly, just follow those 2 simple rules. Find average, find uncertainty, and you're ready to present your data. All right. So what we have next is this. That means, for example, I'm going to just make up some numbers. So let's say you calculated the length, you calculate the width, and then the width, for example, is 38.22 plus minus 0.05 centimeters. So that's basically the average and uncertainty for the length and the width. So that means you can just come to me and say, okay, so those are, that's our result. The next 2 things you want to maybe verify here is it accurate? Is our measurement good or not? The way we will know if your measurement is good or not is by comparing it to some kind of accepted value. So for example, if I have a manufactured value of length and width, that means when this table was built, manufacturer used very precise instrument to measure the length and the width. Let's say I'm going to put like LA as accepted value. So accepted value. Or known value or a theoretical value, sometimes called. Then I can say, all right, so what they did, when they measured brand new table with no scratches, nothing like that, and very precise instrument, they got the value of 82.600 plus minus 0.1. Let's say they got something like this. Okay. And again, you can see, right, there is a standard deviation. There's an uncertainty in their measurements as well, because again, doesn't matter how accurate your instruments are, you're still going to have uncertainty because human is doing that experiment. And, again, even if when the software does or computer does, tiny as the standard deviation, there still will be one. All right, so this is then will be our measured value. This will be our accepted value. What do? We take the average of both, and then we compare. We calculate the error in our measurement. Error in our measurement, which will be, a measured minus accepted. So for example, here it will be 82.300 minus 82.600. So we calculate basically the difference between them. Okay. So what we'll get here, we're going to get negative 0.3. And you're going to ask, how can we get a negative? It's okay, because we can technically use this as absolute value. Remember, if I put it in absolute value, that means measurement can be, just positive. So 0.3 centimeters. What it means here is that the difference between them, right, is 0.3 centimeters. But does it tell you if it's a good experiment or not? Well, not quite. So then what we can do here is we can calculate percent error. So for example, percent error, it would be to take the error and divide it by the accepted value, and then times 100%. So that's why it's a percent. Sometimes this is known, let me put it like this. Sometimes it's known as percent relative error. This relative term means that it's a ratio of error over accepted. So percent relative error. So that's a relative error. Relative error is the ratio of error over accepted times 100%. So we take 0.3 centimeters, which was our error, divided by accepted, which is 82.600 centimeters, and then times 100%. See, the units cancel out because it's a ratio. So if I take 0.3 divided by 82.6, then this times 100. All right, so what I get here is I get 0.4% roughly. That means they are different only by 0.4%, less than a percent. Is this a good experiment? Absolutely. What if my measurement was 4%? Well, it would have been a little bit higher than, let's say, expected for something, straightforward like this. But if it's, let's say, 24% or 34%, now that would have been, relatively poor experiment. 0.4% is an excellent experiment, and that's how you measure accuracy. So then the accuracy is basically in terms of verifying if your experiment is, let's say, close to the accepted value or not, right? So this is basically what we did. We looked at accuracy. Accuracy is something that we're going to be looking a lot in our experimental measurements. Is our experimental measurement usually the average, right, compared to the, let's say, accepted value of the average? And we don't just look at it, okay, here's a number, they seem close enough. No, what we do, we first find the error, and then we find the percent relative error. Using those two tools, we can then be able to figure out if our experiment is good experiment or not. Accuracy allows us to basically verify experimental result.